In this video, we're going to look at solving percent problems. So between 2000 and 2010, global carbon emissions increased about 3% each year. And in 2013, global carbon dioxide emissions were 36.02 gigatons. Okay, so they're going to kind of use this example in a few different places. But let's go ahead and kind of explore what this is talking about. So obviously we're interested in the percent. So first thing they ask is if you have worked with percentages before, let's use the space below to describe how you would find 3% of 36.02 gigatons. How do you actually find that 3% of that amount? Okay, and there's a couple ways to approach this, and I think most people might have it in their heads that you have to actually do a multiplication, and that's true. Percentages are typically multiplied. So in this case, what we're doing when we're taking 3% of a number, we need to rewrite 3% into a form that's useful. So we've talked about percents, so let's write it as a decimal. So 3% is the same thing as 0.03. So if I take 0.03 and then times it by 36.02, and I'm going to grab my calculator, you grab yours too, maybe pause the video, whatever you need to do. But I'm going to do 0.03 times 36.02, and I came up with 1.0806. And that is how I take 3%. There is another way that a lot of people like to work with percents, and that's writing it as a fraction. So as a fraction, 3% is 3 over 100. And instead, I could multiply 3 over 100 times 36.02. Now, the way you would do that multiplication, and it's probably been a while since you've worked with fractions, so I will refresh your memory. We can place this over 1, and then we would multiply straight across. We would do 3 times 36.02. So let me do that on my calculator. And I get 108.06. That's an 8. Kind of disconnected there. And then 100 times 1, which is just 100. And now I divide that. And when I divide that, that gives me the same answer of 1.0806. So there's two ways to approach it. Now, using the calculator, the easiest way would be the decimal. But there are definitely applications with fractions that are kind of nifty that we may want to explore in this section, which is why they wanted us to think of it both ways. Okay, so now they're asking the question, if global carbon emissions increased by 3% after 2013, what would we expect the actual global carbon emissions to be in 2014? So in 2013, it was this number of 36.02, and they want to know what it's going to be in 2014. They don't know that, but we know it increases by 3%. Well, we just found 3% of 36.02. So we need to add the 3% we just found. So we're going to increase this by 1.0806. So 36.02 plus 1.0806 comes out to, oops, I just realized I plugged in my number wrong. 1.0806 plus 36.02. There we go. All right, now I'm getting 37.1006. So that would be what we'd expect the global carbon emissions to be. All right, and then they actually give us the actual number. In 2014, it was 36.27. So it actually didn't increase a full 3% that year. That's nice. There was a slight drop, but that was kind of the prediction up to that point. Okay, let's look at another example. So this particular book has been adopted by Lane Community College. So you'll see Lane Community College actually referred to in the problems multiple times. That's fine. So they said 13% of community college students have children. That's a general statistic. So if at Lane Community College, there is 26,176 students, how many of them would we expect to have children? Okay, so they're going to approach this problem 3 different ways. The first is a visual representation. If we think of this block as representing all of Lane College, then how many students is represented in each little square? So this block is representing a percent. In this case, it's representing 13 out of 100. So there are 100 little squares total. It's a 10 by 10 little square. So each of those little squares is going to represent a certain amount of students. If the total population, and here I want to kind of zoom in a little bit while I'm doing this. If the total population for their students is 26,176, then each little square, one square, is going to equal 26,176 divided by 100, because it's broken up into 100 little boxes. All right, and doing that on my calculator, I get 261.76, or I could say it's approximately 262 if I really wanted to, but I'm going to leave it like that. I'm going to leave it as a decimal, because then they ask me to say, okay, so if that's how much is in each square or box, then the 13 little squares that are actually shaded, I could figure out how many students that is if I'm adding up 261.76 13 times. Or in other words, I'll just multiply this by 13. So 276 point, oh, sorry, wow, I'm having some definite trouble plugging into my calculator tonight. 261.76 times 13. I am getting, and here I'm going to put it down here just because of space, 3,402.88, which as a final answer, I should just say 3,403, because we're talking about students. That's how many students I would expect to be or to have children at that college. Okay, so there is another way to do it, and that's using proportions. That's working with the fraction version of the percent. And as you can see, what we're thinking of it is setting it up as a part to a whole. So in this particular problem, what we're given is the whole student population. So that would be this 26,176 in the denominator, and we don't know the part. So I'm going to go ahead and call that X. And now we have a proportion, which we worked with in the last week's homework. So to solve it, I'm going to cross multiply. So I'm going to multiply 13 times 26. Oops, I'm so sorry. That's so sloppy. 13 times 26,176, which on my calculator, I get 176. 340,288. And then I'm going to set that equal to the other cross multiplication of 100x. And then to solve for x, I'm going to divide both sides by 100. So 340,288 divided by 100 is going to be 3,000. Here, I'm kind of running out of space here. 3,402.88, which I'm going to round to 3,403 since we're talking about students. That would be X. All right. So there's 2 ways to solve it. One's visual, one's using proportions, which we talked about. And then the other way is to kind of create a multiplication. So if we are finding 13% of 26,176, of in this context means multiply, convert 13% to a decimal, and then multiply by 26,176. So converting 13 to a decimal is 0.13. And then timesing that by 26,176 I get 3,402.88, or of course, I'm just going to round that to 3,403. So there are three different approaches to the problem. So many percent problems can be solved using this proportion, which we used in part B above, where you put the percent over 100 equals part over a whole. And then they also mentioned you can use pictures, and you should consider trying using more than one method. And that helps you to verify that you're getting the right answer. Okay, so let's suppose the whole amount in this square is 600 students, okay, taking a particular course this term. So how many students are represented in one box? Just like before, since there are 100 boxes total, I'm going to take 600 and divide it by 100. So one box equals 6. So every box on this equals 6. So fill in as many boxes as necessary to represent 54 students. And then they say, okay, how do you know how many boxes to fill? Well, 54 happens to be divisible by 6. So if I take 54 and divide it by 6, that's going to give me 9. So that means I'm going to fill in 9 boxes. All right. So here, now I'm definitely going to zoom in a little bit more just to do this. And because I'm working with this tiny little pen here, mine is not going to be hopefully as pretty as yours, but there we go. There are my 9 shaded boxes. And what that tells me then is the percent of students that are represented here as 9%, that is 54 students. So we learned that 54 of these 600 students are at least 60 years old. So that represents 54 people that are at least 60 years old, which is 9%. So the percent of students is 9%, because from the picture, from this box, this percent box, 9 of them are shaded. That's where the 9% is coming from. Here, I'll even draw an obnoxious arrow just to make sure that that hits home, because I really feel like I said that very poorly. All right, let's try another one, shall we? All right, this time our square represents 450. And they say, what is 1% of 450? So if I were to shade in one box and one box alone, that's 1%. So they're basically asking me again, what is one box? Okay, so I would do 450 divided by 100, which will come out to 4.5. So 4.5, and that is one box. Now, there is another way to find 1% of 450. And here I'm going to do that in green. And my green is kind of thick. So here, let me decrease the thickness on that one. So I could take 0.01 and times it by 450 on my calculator. And so here, I'm going to put the word or, because this is an alternative way to do it. And that comes out to 4.5. And again, because 1% is represented as one box, that's how we're saying this is just representing one box. So that's another way of doing this. Okay, so find the amount of money that would be represented by 19 of these boxes. Okay, so 19 of these things. That means that I'm shading in 19. And in fact, I'm not going to take the time to actually do all the shading here, but I'm shading in 19 of these. And that would mean then that to find out how many of these there are, I would take 19 and times it by 4.5, because each box represents 4.5. So I'm doing 4.5 19 times. Okay, so 19 times 4.5, I'm doing that on my calculator, and I came up with 85.5. So 19% of 450 is 85.5. By the way, I just realized they've been using dollar signs. I probably should have been using dollar signs too. So this would have actually, in terms of dollars, would have been 450, right? And this in terms of dollars would have been 85.50. But there we go. And the answer is this amount represents 19% of 450. And they say, why? Why is that? Well, that's because since each box is 450 and we have 19 of them, we're basically adding 4.5 19 times. So we are adding 4.5, 19 times. All right, so now they're saying use the model to determine 72% of 450. Okay, well, again, 72 means we're shading 72 of these little boxes. And if each box represents 450, I'm just going to take 72 and times it by 450 or 4.5. I'll just call it 4.5 for right now. But it is 450, and that comes out to $324. Here, let me put a little box around these. Should have been boxing my answers just to make sure you know that those are the answers to the question. Sweet. All right. How would you show $75 using this model? So how would we figure out what percent $75 represents? That's what they're kind of asking us, 75. So what we would want to do then is if each box is 450, we're going to want to divide 75 by 450. And that comes out to 16.666666 all the way to 7. So it's 6 repeating. Okay, I'm just going to go ahead and write 16.7, and that would be percent. So that would be the percentage representing $75 in this particular model. And then what percent? Oh, that's funny. There it is. I just answered that question. All right. Boom. Okay, let's try another one. This time, our box is representing. Oh, we don't know what the box is representing. We're told that that is the number of students enrolled in a summer chemistry course, but the shaded boxes are 64. So how many total students were originally enrolled in this summer chemistry course? Well, it's a very large course. Let me start with that. So that box is 64. So what percent is that 64? That's the question. So if I counted all of these boxes, it looks like there are 16 boxes. And those 16 shaded boxes represents 16%. Okay. Now that I've kind of determined that, since there's 16 boxes total, and this is a total of 64, each box then is representing how many students. So that I would take 64 and divide it by 16 boxes total. So there's 64 students represented, divided by 16 boxes, and that's going to come out to 4. So each little box is 4 students, which means 4 times 100 is 400 students total. In that chemistry course. All right, institutional data analysis shows that 16% of students in the summer chemistry course drop or withdraw from the course. How many of the originally enrolled students completed the summer chemistry course? And what percent is this? So if 16%, if this is actually the number of students who've dropped the class, then how many students are going to be left? Well, as a percent, that would be 84%. Why? Well, if this is a total of 100% and this shaded box region is representing the withdrawal students, then the white region is representing all the students who stayed in the class. And there are 84 of those little white squares. So 84% is what's left in the class. And then the number of students that are there is 4 times 84. Sorry, my dog just barked in the background. Hopefully that wasn't too loud. 4 times 84. Wow, it doesn't want to let me erase. Okay, I give up trying to erase. 4 times 84. Okay, there we go. I got to finally fix it. And I zoomed in a little bit. Okay, so 4 times 84 comes out to 336. So that's how many students stayed or completed Sorry, I was rereading the sentence. Complete the course. And that represents 84% of the total. Okay, so then they ask us to do some illustrating using these decimal squares, which are also called percentage boxes. Okay, so 0.5% would be half of a box. Now I'm going to have to definitely zoom in for this. So half a box. All right, I'm going to try. I'm going to cut it in half like a diagonal because I'm hoping that'll be a little bit easier for me. Boom. There's 0.5%, half that first square. Okay, 5% would be represented as 5 of these squares. All right, there we go. 50% would be half of them. Now, this is me being really lazy, but that's just because it's hard for me to draw this with this little setup, but that's okay. You can be lazy with me too. We could pretend that half of those then are shaded. And then 100.5%. Well, in order to do that, we'd have to add, so it'd be this entire box, fully shaded, plus an extra half square, which I drew with that diagonal earlier. So there I'll represent it. And of course, this is all supposed to be shaded, even though those just look so sloppy. All right, best I can do right now. There we go. Go ahead and zoom back out. But these kind of representations can be really helpful for very visual students. Okay, so what is the difference between 0.5%, 5%, and 50%? Well, 0.5% is representing less than 1%. Okay, but 5% is representing, in these pictures, 5 out of 100. 50% is representing 50 out of 100. So if we wanted to do the 0.5% out of 100, I can do that. It's going to look like this, but I'm not going to leave it like this. 0.5 out of 100. Okay, but having a decimal there is a little bit weird. The way you fix that is you multiply the numerator and denominator by 10. And if you grab your calculator and do that, basically all it does is move the decimal and put that over 1,000. So here's the difference. This is 5 out of 1,000 versus 5 out of 100. And here, this can actually reduce to 5 out of 10. And we have a 5 in common with each of these. That's kind of nifty. So 5 out of 1,000 versus 5 out of 100 versus 5 out of 10. Now, all of these numbers do reduce even further as fractions. Just to comment, this would actually reduce to 1 out of 200 versus 1 out of 20 and 1 out of 2. So that's another way of thinking at it about all three of those representations. And then how do you represent each of these as a decimal? Well, we did that before when we reviewed percents. We just move the decimal twice to the left. So 0.5% would be 0.005. 5% when I move the decimal here. Sorry, I should have like that, right? 5% when I move the decimal would be 0.05. And then 50% when I move the decimal ends up being 0.5. So we have fraction representations or we have decimal representations, and we can kind of see that the further that 5 gets away from the decimal, the smaller the amount we're looking at. How would you show more than 100% using decimal squares? Well, you have to add another set. You would need to add another decimal square. Now, I didn't do that in that problem up here where they asked us to do 100.5%. I just threw on a little half square. That's really kind of not what they were after. They would have liked me to have added an entire decimal square. I wasn't going to do that because that would be very hard for me to draw. But that's really what you would do. You would have to add another one in order to represent anything above 100%. Okay, so a total of 9 9,855 million metric tons of carbon were emitted into the atmosphere in 2014. This represents 127% of the carbon emitted in 2004. Okay, so unfortunately, the problem kind of went to the next page. Use the model to determine how many million metric tons of carbon dioxide are represented by 100 boxes. Okay, so they had to do 2 decimals. And as you can kind of see, when this formatted into Word, it kind of got a little kooky. So I apologize. I didn't catch that before I started recording. You can just bear with the fact that it looks a little dumb. So we had because it's 127% increase, right? 127%. That 27% increase needs a separate decimal square, okay? So they're saying, all right, well, if this is representing 9,855 million metric tons, that's how much it's representing shaded regions, and that's 127 shaded regions to figure out use the model to determine how many metric million tons are represented by 100 boxes. So let's figure out how much one box even represents. So one box is going to be this 955 million divided by 127, because that's how many shaded boxes there are. And I grab my calculator, and I'm getting 77 we'll say 6. So one box is 77.6. So 100 of them, that's going to be 7760. So 7,760 million metric tons. So tagging on that units of measurement. And that would be the answer to part A, but you do need this to do it. Over here. Okay. We could say that there was a 27% increase amount of carbon in the atmosphere. Oh, I'm sorry. We could say there's a 27% increase in the amount of carbon in the atmosphere from 2004 to 2014. How does this model show it? Well, the separate, the additional box, the additional decimal square shows the increase. So if that's the increase into 2014, then what it increased from was this. This then is representing the 2004 amount, and that's what they're asking in part C. So we start with this 7,760 million metric tons. That's the 2004, and then we had a 27% increase into 2014. So 2004 is basically that first box plus the 27% increase. Now, describe the values in a sentence of 9,855 and 7,760. Use the words unit and percent in your sentence. This is putting the value in context. So we would say that 9,855 is a 27% increase in, sorry, I want to use the same, in million metric tons of carbon, increase in million metric tons of carbon from 7,760 million metric tons of carbon in 2004. And let's write out 9,855 million without words. In other words, really what that represents when they say 9,855 million, it means you need to add 6 zeros, because That's million is 6 zeros. Okay. So how that's really representing billions. So this is actually 9.855 billion. That's another way of saying that. And then the gigatons. Now, gigatons is representing a billion tons. So when you say 9.855 billion metric tons, you could just say 9.855 gigatons. Because each ton of carbon is equivalent to 3.67 tons of carbon dioxide, multiply your answer from part E by 3.67 to get the emissions of actual carbon dioxide. So 3.67 times part E. Okay, so I guess I'll use the 9.855. So 9.855 times 3.67 comes out to the 36.16785 that we'd seen at the beginning of this activity. And they just kind of wanted to pull it together for you, this kind of discussion of really how big these numbers are that they're actually, in fact, talking about when we're talking about the carbon dioxide. And that's it.